Hi, everyone. My end of that story is I was procrastinating hard. Is a really, really much better use of time than studying. So, my name is Ben. I do consulting around high-performance data analysis. So, what that means is I write code for data analysis and optimization problems that have hard constraints on how fast they have to run. In some cases, that's 10, 20 millisecond response time. In other cases, that can be a couple minutes because someone's sitting at a dashboard and clicking refresh. I'm going to walk you through my workflow when it comes to speeding up code. All of this advice is stuff that I've done in production, and all of the samples are adapted from live code. I've also been led to understand that this is an R conference. So if you don't use Python, don't worry. The code is really easy to follow along with, and most of the advice is generalizable. OK, so the first misconception that I want to clear up is Python is fast. Lots of people think of Python as slow, and natively that can be true. If you're just writing pure Python code, that can be 10 to 100 times slower than C. The advantage is it has really good C interop, so you can use C for all of the slow parts. In particular, you can use a lot of C that you don't have to write, which is great. I don't know if Wes is in the room? No. No? OK. Wes, one of the presenters yesterday, wrote pandas, which has a lot of the same functionality as R, mapped to Python. It's super fast. He's saved me lots and lots of hours of work over the past few years. Also, I'm going to be covering a lot of stuff. There's no time for Q&A, but I'll be around. Feel free to come up and talk to me after. Unless you know how to do performance optimization, in which case I'm not going to be covering very much at all. OK, so before you try this at home, the obligatory quote is, "Premature optimization is the root of all evil." This is from Donald Knuth. Basically, optimizing code is really fun, but you don't want to sit there and write really, really clever code unless you have to. If you're about to start optimizing something, make sure you know how fast it's supposed to be. And remember that making something faster is trading off against your time, the time you're spending developing it, trade off against readability and maintainability. If you have something that takes 2 minutes to run and you're writing 200 lines of code to speed it up by 5 seconds, it's probably not a great use of time. OK, general optimization, sort of best practices. Profile your code. 95% of your code is irrelevant to your performance. Your computer does around 3 billion operations per second. If you have something that's running for 10 seconds, unless you wrote 30 billion lines of code, most of that stuff is going to be coming from loops, stuff that's done over and over and over. You want to focus on those loops, and they're not necessarily going to be where you think they are. In particular, with a high-level language like Python or R, it's not always possible to predict what exactly the machine is actually doing. In Python, there's a really nice tool called cprofile. It will give you run a piece of code, it'll analyze all the function calls, how long they take, and you basically use this output to figure out what's going on. There's an example here, and there are a few different columns. All of them are important. There's the total time that the function took, the time it took per call, and the time that it took excluding sub-functions that it runs. All of this stuff is pretty important, and it can help you catch different things. So if you have a loop that's iterating 1,000 times, and you see that something is being called 500,000 times, you probably have some sort of quadratic behavior that you didn't want. If one particular function is taking a lot of time, it's helpful to look at it and see, maybe I don't need to be running this as often. Maybe I can speed this up. Maybe I can run this calculation once and refer to it later. Maybe I can replace it with an approximation. Basically, this is where you start. The number one thing you don't want to do is sit down with a slow piece of code and just start changing the things that you think you can make faster, because that's like a really great way to spend an afternoon and get nothing out of it. I'm sure R has something like this. One quick note for Python. There's a version called Profile. It's a lot slower. It gives you better introspection into the code that you're running. But if you don't need that, don't use it. If you're not sure whether you need it, you don't. Stick with C Profile. It's way faster. OK. You've identified the slow part of your code. Now what do? This is where the coding interview prep that you've all done to get your jobs is going to come in handy. OK, a little too soon for some of you, I guess, for that joke. Make sure the big O performance bound is optimal. If you have something that's being done in a loop, all of the code that you're looking at is going to be in what's called hot loops. Then see if you can take some of that stuff and move it outside of the loop. If you're doing the same operation a million times, that's bad. Use caching for repeated calculations. And those three are pretty standard. One piece of advice that's pretty general but isn't applied as often is apply algebraic simplifications. So outside of data science, this doesn't come up as often. But when it comes to data science, you know all sorts of things that your computer doesn't, like math, algebra, and calculus. In some cases, you can do something sort of there's compile time optimizations in C. You can do like programmer time optimizations if you actually apply the math and stats that you guys know and pick something better for the computer to be doing. The absolute most common issue I see is code that's accidentally quadratic. Can anyone tell me what's wrong with this? Reallocates the array every time. No. OK, good guess, though. So this is scanning list 2 every single time. So this is running in quadratic time to compare 2 lists. Python has something called a set, where you can check if an element is a member of set in constant time. So this seems really basic, but this is literally the thing that comes up most commonly. There's usually a bunch of code in between sort of the top part of this function and the bottom part of this function, so it's not really this obvious. But really frequently, this is the issue. There's a really great Tumblr called Accidentally Quadratic that talks about this coming up. That's also the first time I've said really great Tumblr in a conference talk. But I would definitely recommend checking it out. Stuff comes up from Linux, from production systems, from Rails, all sorts of things where you think it wouldn't happen, but it's really easy to slide into. Okay. Next up is business logic. So algorithms courses and problems are all really neat, but the reality is a lot of times you're going to be running some sort of simulation that's NP-complete or just possibly like polynomial, but very, very slow. Sometimes thinking about the business end of things will tell you stuff that just pure computer science can't. And I know that was a shock to me, too. Looking at the business end of things can give you heuristics or other optimizations where it's not necessarily something that drops out of the theory, but it lets you know that there are certain scenarios you can ignore, and it might make a computationally intractable problem approachable in practice. OK, cool. Right on time. Python-specific optimization. The reason that I really like Python for data analysis is that you can build your entire program in it. If you're deploying a web app that's maybe doing something that Shiny can't, maybe interfacing with a larger code base, you can build it all in Python. And it has fantastic, fantastic libraries, as I mentioned earlier, that do a lot of the heavy lifting for you. So the first step is use highly optimized C code that somebody else wrote. I can't emphasize how important this is. NumPy, SciPy, Pandas, and scikit-learn are all fantastic libraries. There's a lot more in the ecosystem, but I highly encourage you to look into it if you haven't looked at Python before. If you're doing something relatively standard, odds are it's implemented already, and it's very fast, and it's correct, which is also not something you can take for granted. If you're building something a little bit weirder, or esoteric that just hits on your use case, see if you can combine the built-in stuff instead of writing everything from scratch. See if you can take a more general approach that maybe theoretically is going to be is going to be slower and require more computations, but in practice, the implementation that scikit-learn has is so good that it doesn't matter, and see if you can adapt it to your use case. The most maintainable and most performant code is the code that you don't have to write. Okay. Next step. You've exhausted the libraries. You still have some custom stuff that you're doing, things that are written in pure Python. How do you speed it up? A couple of basic tips that I find counterintuitive. Function calls are really expensive. Avoid them and avoid recursion. I particularly have a hard time avoiding recursion because I think it's very natural, but it's super slow. Just change it to be imperative, even if it makes your code look less nice. Make sure you know the runtime of the data types you're using. So what I showed you before with the quadratic list, that's an example of this. If you're using a Python list and you're inserting a bunch of stuff at the beginning, that's going to be quadratic. That's something else you want to avoid. And again, this seems really obvious when I'm standing up here and saying it, but when you're writing code, like if you have a piece of code that looks like it should be fast and it's not doing that much and you just don't know what's going on, it's probably something simple like this, right? It's probably not some sort of like Fields Medal worthy insight that you need. It's probably like, oh, I forgot that you don't want to prepend to lists. More obscure things, make your variables local. Because of the way Python's structured, it's really expensive to look up global variables. And use map, filter, and reduce instead of for loops. Those are written in C. They're really fast. Those are written in C by the creator of Python, so it's not quite a library, but the previous comment on using other people's code still applies. There are a lot of other tips, a lot of them published by the guy who made Python online. Would highly recommend you Google them if you're doing this sort of stuff. Okay, next step. You've exhausted that list. Now you're mixing libraries with your own code. This is where things start getting kind of brittle and unmaintainable. So again, before you get here, make sure your code is working correctly. Make sure you have tests so that you know you're not speeding it up by returning the wrong answer, which is really easy to do. Okay, so step one, vectorize. Use NumPy arrays and matrices wherever you can. They are much faster than built-in lists. Here's an example from some simulation code that I have that, again, simplified, but this is a real-life example. So instead of using a list, you immediately convert it into array. Everything you're doing is done in an array, and you use array functions to get back the answer. Another issue here, allocating arrays can take a really long time. If you have a loop that's run over and over, consider moving the allocation outside of the loop. This is something you normally don't have to worry about in Python explicitly. So for those of you who don't know exactly what array allocation means, Google it, and there will be a good explanation in C. But this is basically an example where over here, each time you're going through the loop, you've got a new array of zeros being allocated. At the end of the day, that comes out to about a terabyte of RAM that your computer is passing back and forth. It's a lot faster to pull that out. In the case where I had this, the computer was spending more time shuffling the zeros around than it was doing the actual calculations. OK. Last resort, C. If this talk had been entitled High Performance Python, How to Generate Job Security, this would have been at the top of the list. So Python is awesome. It lets you inline C code directly into Python. It looks a bit like this. So this is a piece of code that finds the first Fibonacci number that's greater than or equal to n. Written in pure Python, this is relatively slow. This is a piece of code that does the same thing, but does it a lot faster. So the way that Python works is it lets you, it compiles your code, and it allows you to tell the compiler certain things that you would normally tell it if you were using C, which is this is an integer, this is a float, that sort of stuff. And that lets it drop down and write much faster instructions on par with C instructions than you would normally get. The other option is C extensions. So this is really just writing C code and passing it back and forth. This can be very effective, but you can definitely go overboard with it. You should limit these techniques to really very hot loops. You should make sure that all the code you write this way is modular and out of the way of your main code base. You don't want just C fragments floating around everywhere, because then that's very difficult for anyone else to work on. And the next person working on it might be you in 3 months. OK. Couple of things I haven't mentioned. Multi-threading. Most computers today have the mentality of buy one core, get 7 free. Python doesn't really acknowledge this. So I don't know what the situation is with R, but with most programming languages, multi-threading is super important. Python basically just doesn't do it. Notable exception is some of the libraries that are written for it in C do it. So scikit-learn is a good example of something where most of the major algorithms you're using will enable parallelization. I was working on random forest recently, and I missed that there's an option to pass to use all of your cores. And I added like 3 characters to my code, and it ran 8 times as fast. So that was great. So again, this applies to stuff you're writing, but insofar as you're using stuff other people have written, you might be able to get full performance. There's another thing called PyPy, which is a Python JIT compiler. If those words don't make sense to you, it's kind of outside of the scope of the talk, but it's extremely cool. If you are interested in this sort of thing, I would highly recommend reading about it. Unfortunately, it's not compatible with NumPy and a bunch of the other things I've mentioned, so it's not quite something you'd want to use unless you're sure you don't need the other stuff. But if you do use it, it's super fast, which is great. Okay. Optimization is really addicting. I've spent many a day where I've just been sitting and you change a line and you hit a button and you see a faster number, and I spend the entire day optimizing the back end. And there's probably higher value things I could have been doing, like writing a front end so someone could use my code. So this is one of the reasons why it's very important to have an outside metric for how fast your code needs to be. The answer is almost never as fast as possible. The answer is usually, well, we've got people looking at this, and so it should really return in about half a second. Or someone at the other end needs to pick up a phone and call somebody with this output. That's pretty rare, but something I had with one of my clients. And then, if something takes 10 seconds to run, it takes 10 seconds to run. OK. Summary. So avoid premature optimizations. Have objective benchmarks that you want to hit. Profile your code. You will not be able to accurately guess where your code is slow. You might have a general idea, but there's no excuse not to run a profiler. And as I've said, the gold standard for performance is C code that you did not have to write. OK, this is a very deep topic. Some resources, general resources, I really like the book Programming Pearls by John Bentley. It gives a good overview of how to start thinking about these things and other engineering concerns. Accidentally Quadratic Tumblr, fantastic read. If you want to get very deep into how to make things run fast, MIT OpenCourseware has Performance Engineering of Software Systems, or 6172. It's a series of video lectures. Would highly recommend it. It's like You can if you watch like one video a day during lunch, you can get through it, within a couple of weeks. For Python-specific stuff, look up cprofile, look up Cython, and look up Guido's advice. That's one of the posts that he's had. That's it's a case study, so I really like it. If you just Google it, there's a couple other things he's written over the years. If you find something from like 2004, it might be out of date by now, though. So keep that in mind, and there's stuff floating around. I'm Ben at caffeinatedanalytics.com. I'll be around, and come talk to me if you have any questions.